So this is the video that we watched in class to begin with um, geometric sequences. We talked about arithmetic, which is where they're adding and subtracting. So this is, if you can't really see the video very well, you can type in lily pad escape through Google and you can watch this video. It's the first link that comes up. So here it is. Okay, so from here, we watched pretty much the whole video on that to finish it out. So what we did with that is, since it started with one lily pad and then it doubled, so then there were two lily pads, and then the two doubled and we got 8. Or sorry, two doubled and we got 4. 4 doubles we get 16. 4 doubled we get 8. 8 doubled we get 16. Okay. So what this is actually doing, doubling is the same as multiplying the number before by 2. Just like tripling would be multiplying by 3 and so on. So in this case, we are talking about sequences that are geometric because it's timesing and it's not adding and subtracting. So what you come up with here is 1 times 2 gives you the 2. 1, then you take the previous, so what we had here, and we're going to times by 2 more to get us 4. And if we keep going, we're going to times by 2 more to get 8, and so on. So I'm just going to write it one more time. Timesing 1 more 2. Okay. We talked about how repeated multiplication is, repeated addition is multiplication. So if I have 4 plus 4 plus 4, that's the same as 4 times 3. However, if it's 4 times 4 times 4, that's exponents, and it's 4 to the 3rd power. So what we're dealing with here is this becomes 1 times 2 squared. 1 times 2 to the 2nd. This one, 1 times 2 to the, okay, I missed that. 2 squared, 2 to the 3rd, 2 to the 4th. And then that pattern is going to continue. So 1 times 2 to the 5th. Technically, we don't have to times by 1. We can just say 2 to the 6th, and then 2 to the 7th. So this one, if we come back to that first one I had up here, this is 2 to the 1st power, and then if you go back 1, notice that here's 1, here's 2, here's 3, here's 4. So if we're going back 1, this is going to be just 1 times 2 to the 0, actually, because you're going back 1 on the exponents. And any number to the 0 power is 1. So that's why 1 times 1 gives you the 1 there. So for a geometric, the explicit form is actually f of n equals f1 times r to the n minus 1. Sorry, hopefully you can see that. So for our pattern here, I gotta erase some of this. For our pattern, we have Fn, and just like here, we've got our first term, which is 1, times that R is the ratio, which is also known as the number that you're timesing by. So we're timesing by 2, so R is going to be 2, and then to the n minus 1. In this case, I called it x, but we could have called this n. And if you look over here, if we do 3 minus 1, that's where the 2 is coming from. So then again, if you do 2 minus 1, you're going to get this 1 right here. And that works. That works throughout this whole thing. So if we got 4 minus 1 gives you this 2 to the third here. Sorry, you can't see that. And then let me just pick a different color. So we got 4, and then that's 2 to the third. 5. So 5 minus 1. So this is 2 to the fourth. And so by minusing 1, it's actually working out for our pattern. So just like here, how if you're going to use f of 1, you have to minus 1. If you actually end up using, let's say, f0, technically you don't have to minus 0 because it's just going to stay n. So yes, you can use different term numbers, just like arithmetic we did different terms, but typically we'll just use the first term. So then from here we went and we reviewed what we did today in class, which today I mean the 5th of November. And we reviewed another arithmetic sequence just so we don't forget it. Here we've got 4, 6, 8, 10, and then figure 5. I'm not going to draw it because you can see that it's going to be 12, and there will be 2 out front, and then the 12. I don't think that's 12. I need 2 more, but you get the idea. So write the explicit form and simplify. So because this is actually adding 2, then the explicit form is going to be the arithmetic function. So that would be f1 plus m times n minus 1. That is arithmetic. So in this case, we have fn equals, f1 is 4, that's our first number, plus it's adding 2, so I'm going to plus 2, and n minus 1. It says to simplify this, so I'm going to distribute the 2, and I'm going to write that up here. So we're going to have 4 plus 2n, and then 2 times negative 1 is minus 2. If I combine like terms, then f of n is really equal to 4 minus 2 is just 2, so it's 2n plus 2. That would be our simplified form. So let's review geometric from last time. The pattern here is timesing, even though some of you might think it was adding 5, but no, it doesn't say 5, 10, 15, 20. It's actually multiplying by 2. 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40. So explicit form, if we're multiplying, that means it's geometric. Geometric looks like this. F of 1, just like we learned with the lily pads, r to the n minus 1. So for our function, we're going to have f of n equals f1, which in this case is 5, times our r in this case is 2 to the n minus 1. So that's our explicit form right here, explicit. Recursive would be, the general form is fn equals r the number that you're timesing by, times the previous term. So what do you times by to get the next number? So recursive is fn, not r, fn, and then it's 2 times the previous term. The most mistakes I see is that this n minus 1 is, a lot of people don't put it as an exponent. But because this is repeated multiplication, 2 times 2 times 2, we keep repeating that, it has to be an exponent. So let's talk about the graph. I'm going to erase what I've written up here. Hopefully you don't, if you can stop the video if you need that. And we've got, if I want to graph this, I can make a little table if we want to. I got 4 numbers, so 1, 2, 3, 4, and 5, 10, 20, 40. So I'm going to go by tens, 10, 20, 30, 40. When you're writing this, please label your scale. We got 1, 2, 3, 4. So I'm going to go over 1 up 5, over 2 up 10, over 3 up 20, and then over 4 up 40. And so what happens with geometric functions is they actually curve. They are no longer straight. Straight is only when it's adding or subtracting. Okay, so another example, even though I need to switch these numbers, this should have been 18 and this number should be 54, and you'll see why. The reason why is because if you go from 2 to 6, that's adding 4, but 6 plus 4 is not 18, so we know it's not adding. It has to be multiplication. 2 times 3 gives us 6, and then 6 times 3, and then times 3 is the 54. So this is, again, geometric. So we're going to have fn. The first term is 2, so I put 2 first, times our r, or the number we're multiplying, is 3, and then to the n minus 1. Again, technically I didn't have to put the first term, but if I put, say, the fourth term, and I put 54 first times 3, I'd have to put n minus 4, because that's the fourth term. So yes, you could do that, but or you could just stick to using the first term. Recursive, we got fn equals the number we're timesing by times the previous term gives us the next number, and that's it. If we're going to graph it, we could go by tens, 10, 20, 30, 40, 50. So we'll go 1, 2, 3, 4. We have 4 numbers. I'll go over 1 up 2, over 2 up 6, over 3 up 18, and then over and up 54. So that's up there. And again, we're going to get this curve line. And that's about it for geometric. I guess we could do another example if we're wanting one. Let's do one more. How about, let's do a negative. If you do negative 3 and let's say negative 15 and negative 75. So this is actually multiplying by 5 here. So times 5. I hope I did 15 times 5 correctly, so just hang on a minute. Okay, so 75, yes. So times by 5. So geometric, so we'll have f of n. Our first term is negative 3. The r is 5 to the n minus 1. So that would be explicit. Recursive would be fn. And then the number we're timesing is 5 times fn minus 1. And those would be our equations. This one's actually interesting if you were to graph it, because Um,